Hello, good morning, everyone. Good morning, everyone. All right, welcome to the FREEBASICS series, lecture series. Um, Here in the last lecture, if I remember correctly, we were speaking about what is the acceleration of the center of mass. And we were talking about the positions of the center of mass, the velocity of the center of mass, and uh, this was the last one, which is the acceleration of center of mass that we have calculated. All right. So let's look at the possibilities of what happens when the acceleration of center of mass is zero. That is, the net external force on the system becomes zero. Then what are the different possibilities that happen? That let's look at that. So first of all, let's go back to this situation here where we have calculated the velocity of center of mass, or even the position of center of mass, right? Even the position of center of mass. So in the position of center of mass, we have said that this is the position of center of mass at any given instant. Right? This is how we calculate the position of center of mass at any given instant. If let's say the individual masses keep on moving, right? So if the individual masses keep on moving, then we can say that the center of mass is also getting displaced. The center of mass is also getting displaced. Now, so if the center of mass is displaced, right, I would say that displacement takes place because of the displacement of the individual particles. All right. Now, let's get back to the last discussion that we have done about the acceleration of center of mass. So the acceleration of center of mass states that the summation of all the external forces acting on the system, summation of all the external forces acting on the system will be equal to the total mass of the system into acceleration of center of mass, right? That is the net force acting on the system. This we have stated as Newton's law for system of particles. Now let's talk about the case when the net external force acting on the system is zero. Let's say if summation of all the external forces acting on the system is zero. All right. If summation of all the external forces acting on the system is zero, then it implies that the acceleration of center of mass is zero, right? It implies that the acceleration of center of mass is zero, which in turn implies that the velocity of center of mass remains constant. Which implies that the velocity of center of mass remains constant. If the velocity of center of mass remains constant, if the velocity of center of mass remains constant, then there are two cases, right? Then there are two cases. For the velocity of center of mass to remain constant, then there are two cases. That is, velocity of center of mass can be constant and non-zero. So it could be velocity of center of mass is constant and zero. That could be case one. And then there could be case two. where the velocity of center of mass is constant and non-zero. All right, so these are the two cases that we have. Either velocity of center of mass can be constant and zero, and secondly, velocity of center of mass can be constant and non-zero. Now let's talk about the case where the velocity of center of mass is constant and zero. So I would say that in this case, the initial velocity of the center of mass will be equal to the final velocity of center of mass, which will be equal to zero. Now, since acceleration of center of mass is zero and velocity of center of mass is also zero, I can say, therefore, the displacement of center of mass will also be zero. Therefore, the displacement of center of mass will also be zero because the acceleration zero and the velocity is also zero. So if the acceleration is zero, velocity is zero, then the net displacement of the center of mass will also be zero. Right? This implies that now I know the position of center of mass is summation mi upon summation mi. Correct. It is summation mi upon summation mi. Now, because of that, I can say that if the center of mass is displaced from its position, it's summation mi. If the center of mass is displaced, then I can say the individual particles, the individual particles are displaced. There will be some displacement in the center of mass as well. So I can say displacement of center of mass is given by summation mi si upon summation mi. That is also zero. Right? So displacement of center of mass. This is what the displacement of center of mass is, which basically implies that summation mi si is zero. Summation mi si is zero. Summation mi si is zero. All right. This whole discussion, this is called the mass moment conservation. This discussion is called mass moment conservation. It's called mass moment conservation. All right. Now let's look at the case where I have the velocity of center of mass constant and non-zero. Right here, I can say the initial velocity of center of mass is still equal to the velocity of center of mass finally. Okay, initial velocity of center of mass is still equal to the velocity of center of mass finally, which is non-zero. Okay. So what I can say is the velocity of center of mass. So the initial velocity of center of mass, I can write it as summation mi/ui, where ui or u is the initial velocity of center of mass upon summation mi. That must be equal to summation mi bi upon summation mi. Right? So I can get rid of this. I can get rid of this. Okay. Now what is summation miui? Summation miui is the summation of the product of masses and their initial velocities, right? It is the summation of product of the masses and their initial velocities, right? So can I say that is equal to something like m1 u1 plus m2 u2 and so on? That must be equal to what? m1 v1 plus m2 v2 and so on. Now what is this? m1 u1 plus m2 u2 plus m3 u3 and so on. This is the initial momentum of the system. This is the initial momentum of the system. That must be equal to m1 v1 plus m2 v2 plus m3 v3 and so on. So it is the summation of momentum finally. So it will be the total summation of all the momentum is the total momentum of the system finally. Right? Initial momentum of the system becomes equal to the final momentum of the system in this case. Right? Initial momentum of the system becomes equal to the final momentum of the system in this case. So we can say, that the change in momentum of the system is zero. Change in momentum of the system is zero. Right? Initial momentum of the system is equal to the final momentum of the system, which implies that the change in momentum of the system is zero, which basically is the momentum conservation, linear momentum conservation of system. Right. This is basically the linear momentum conservation of system. So if the external force acting on the system is zero and the initial velocity is also zero, then the mass moment of the system is conserved. Or if the external force acting on the system is zero and the initial velocity is non-zero, then the momentum of the system is also conserved. All right. So these are the two cases when external force acting on the system is zero. Right? We shall talk about all of these things in detail. In fact, in theory of collisions, we have already spoken about this second part. We've already spoken about the second part wherein the momentum of the system is conserved. In absence of any external force, we've already discussed that the momentum of the system is conserved. All right, we have used that in theory of collisions as well. Momentum conservation and everything, we have already done that. All right, so if you have not seen that video, please go and subscribe this channel. This free basics series is brought to you by IITP Classroom. So please go and subscribe to this channel and do hit the bell notification so that you get notified whenever we are live and whenever we upload a new video. You are the first one to know about it. All right. Also, this free basic series is happening every day at 11 a.m. Do not forget to check it out or log in when we are live. So yes, this is about the fact that if the external force of the system is zero, then these are the two different things that can happen. All right, let's try and understand them using some basic questions. Okay, let's say there is this ball of some mass which is projected in this direction with initial velocity u, at an angle theta with the horizontal. All right. Now this mass will follow this trajectory. All right. This is what is the expected path. Again, this is what is the expected path. All right. Now let me give you the question. So that is the complete question. That is the complete question. At the ball, it undergoes explosion due to internal forces when it is at the highest point of its trajectory, and it breaks into two equal masses. Right? If it breaks into two equal masses, it is given that if one of the masses comes to rest immediately after the explosion, where will the other mass land? If one of the masses comes to rest immediately after the explosion, where will the other mass land? So that is the question here, right? That is a situation that we have to tackle. Now, if you read the question carefully, in the first statement itself, they have mentioned that the explosion takes place due to internal forces. That is, there is no external force acting on the system in the horizontal direction. Right. Even during the flight of this individual mass, there was no force in the horizontal direction. Right. So I can say, since there is no force in the horizontal direction, since there is no external force in the horizontal direction, the velocity in the horizontal direction must remain constant. Right. The velocity in the horizontal direction must remain constant. And the center of mass must move along the original trajectory of the particle. center of mass must move along the original trajectory of the particle, right? At least in the horizontal direction. Vertical direction as well, there is only gravity, there is no external force in the in the vertical direction as well. So even after the explosion, the trajectory of the center of mass must remain as it is, right? So I can say since the system does not experience any external force, since the system does not experience any external force, the center of mass of the system follows the trajectory follows the original trajectory of the ball, right? So it basically means that the center of mass will follow along this line and it will finally land here. So this is where the center of mass of the system will be. Right, this will be the final position of the center of mass. Right, this will be the final position of the center of mass. So here, this is where the center of mass is going to lie. All right. This is where the final position of the center of mass is going to lie. Now, since this is where the center of mass is going to be, let's try and find out where the other masses are landing. Right, where the other masses are landing. So let's say the ball undergoes explosion at the top. So this is where the mass was. So it gets broken down into two equal masses, as the question suggests. It breaks into two equal masses. So this mass breaks into two equal masses. So there is one here, and then there is one here. And one of the masses comes to rest immediately after the collision. So if this mass comes to rest at the highest point, it will fall vertically downwards. Right? It will fall vertically downwards. So if let's say the original mass of this ball was m, this is where one of the mass is going to be m/2 is going to fall here, and the other mass would definitely go some distance ahead here. Would definitely go some distance ahead here. Why is that? Because one of the masses is landing just below the explosion, below the point of explosion, and the center of mass is somewhere here, right? This is where the m mass is going to land. So I can safely say that m/2 must be some distance this side, right? M/2 must be some distance this side. So this is how the situation will look like. This is how the situation will look like. So let's say that this is my, let's say this is the y-axis, this is the x-axis, and this is the origin. So the center of mass is at origin. All right. The center of mass is at the origin. Now I know that this distance, the distance between the left m by 2, the left m by 2, and the center of mass, which is basically the final point of the trajectory of the original body. This must be equal to r by 2. This is half the range because this is h max. So from the highest point, point exactly below the highest point and the end of the system, this will definitely be equal to r by 2, right? So the coordinates of this m by 2 will be minus r by 2 comma 0. And I assume that this m by 2 is at x comma 0, right? So I can say finally the center of mass will land at this point, right? 0 comma 0, right? So I can say therefore the position of center of mass, which is the x coordinate here, x coordinate of the center of mass will be equal to m1 x1 m1 x1 plus m2 x2 upon m1 plus m2, right? And this must be equal to 0. Why? Because the center of mass is at 0 comma 0. So I can say m1 is m by 2 into x1. X1 will be equal to minus r by 2 plus m2 is again m by 2 into its position is x whole divided by m, that is equal to 0. So let's take this m here, you'll get it 0. So you get x as r by 2. X is r by 2. That is, it is r by 2 distance away from the end of the trajectory, from the end point of this trajectory, right? So if it is r by 2 away from the end of the trajectory, so I can say this implies that the other mass lands at a distance of r plus r by 2, which is 3r by 2 from the point of projection. This implies that the other mass lands at a distance of 3r by 2 from the point of projection. From the point of projection. All right, you can calculate the range and everything, and you can directly write what is the answer in terms of u, theta, and g and all. You can definitely do that, but that is not required right now. Right? That is not required right now. So this is This is what the question will entail. All right. Now let's do a similar question. Let's do a similar question. And yeah. So that is the question. That is the entire question. That in a situation similar to the previous one, the wherein the mass explodes due to internal forces. So in a situation similar to this previous one, the mass it splits into three pieces. It breaks into three pieces instead of two, and all of these three pieces are equal. Okay, so they get into three equal pieces instead of two. All right, and the velocities of the two of the pieces is given. Velocities of the two of the pieces is given, and we are supposed to find the velocity of the third one. We're supposed to find the velocity of the third one. So the velocity of the third one after the collision is to be found out. Okay. So what we can say is at the highest point, the mass m was going in the horizontal direction, so the velocity given by u cos theta, right? This was before the explosion. This was before the explosion, right? Now, what happens after the explosion? What happens after the explosion? After the explosion, the masses, these masses, they get split into three, and they have the velocities v1 and v2. And I am supposed to find the velocity of the third mass. So it gets split into three. So let's say these are the three masses. They have certain velocities. So let's say this is v1. I do not know where exactly it is. All right. I just know that this is some v1, this is v2, and let's say this is v3. I'm just making a random guess. I do not know if these are the exact velocities or directions. I'm just drawing it at random. Right. So this is after the collision. This is after the collision. Right. Now, since these are the velocities of the masses after the collision, and I've shown what is the situation before the collision, I can say since the explosion occurs due to internal forces, since the explosion occurs due to internal forces, summation of all the external forces, is zero in the horizontal direction, Therefore, momentum of the system in the horizontal direction is conserved. Momentum of the system in the horizontal direction is conserved. Right. Momentum of the system in the horizontal direction is conserved. That is what will happen. Right. If external forces are zero, then we can conserve the momentum. Right. So in the horizontal direction, it is conserved. So what about in the vertical direction? What is the external force acting on the system in the vertical direction? In the vertical direction, there is only one force which is acting on the system. In the vertical direction, there is only one force which is acting on the system, and that is gravity. And the gravitational force is a non-impulsive force. The gravitational force is a non-impulsive force. What do I mean by a non-impulsive force? By a non-impulsive force, we mean that the momentum of the system does not change instantaneously. The momentum of the system does not change instantaneously. That is what we mean by a non-impulsive force. So if the momentum of the system does not change instantaneously, due to a force then the force is called a non-impulsive force. And we can conserve the momentum, or since it does not change instantaneously, I can say that the momentum just before any event can be equated to the momentum just after any event. Because the force is not as large to change the momentum of the system instantaneously. So the force cannot change the momentum, right? So let's say the explosion occurs at t equal to 0. If the explosion occurs at t equal to 0, the momentum of the system just before t equal to 0 and just after t equal to 0 will remain the same. Right? Momentum just before and just after will remain the same. Right? So I can say that momentum of the system just before and just after the collision, we can actually conserve the momentum. All right, we can actually conserve the momentum. All right, so I can say, since in the vertical direction gravity, which is a non-impulsive force, is acting on the system. Gravity, which is a non-impulsive force, is acting on the system. In the vertical direction, gravity, which is a non-impulsive force, is acting on the system. The momentum of the system is conserved or I can say the momentum of the system does not change instantaneously. Does not change instantaneously. So there is no instantaneous change in the momentum of the system. Right? There is no instantaneous change in the momentum of the system. So in the vertical direction, gravity, which is a non-impulsive force, is acting on the system. The momentum of the system does not change instantaneously. Right? Momentum of the system does not change instantaneously. Therefore, momentum of the system in the vertical direction can be conserved just before and after, just before and after the explosion. Right, this is a very, very important step. Right, now we have already established that there is no external force in the horizontal direction. So we can conserve the momentum of the system in the horizontal direction. And right now we have also established that the momentum of the system in the vertical direction can also be conserved. So I can say, therefore, the momentum of the system can be conserved entire momentum. This is horizontal plus vertical. So this is the complete momentum. This is the entire system, complete momentum of the system. Because we have individually identified that it can be conserved in the horizontal and vertical directions. So I can say the complete momentum of the system can be conserved. Complete momentum can be conserved. Let's just write it down. The momentum of the system can be conserved along horizontal as well as the vertical direction. Momentum system can be conserved along horizontal as well as the vertical directions just before and after the explosion. This makes the question very, very approachable, very simple now. So I know what is the momentum just before the collision or explosion rather. So the momentum just before the explosion was m into u cos theta I cap. Right. This was m into u cos theta I cap. This is horizontal direction. And the momentum after the collision will be m by 3 v1 plus m by 3 v2 plus m by 3 v3. So we can equate that, right? So I can say m into u cos theta I cap, that is equal to m by 3 v1 plus m by 3 v2 plus m by 3 v3. So I know what is v1 and v2. I am just supposed to find what is v3. So I can do that now. I can do that now very easily. So I can say 3u cos theta I cap minus v1 minus v2 is equal to v3. That is my final answer here. That is my final answer here. All right. If the values of u, theta, v1 and v2 they are given, we can directly calculate that. And I also know that this is u cos theta is I cap. So all the I cap components will cancel out each other, and all the j cap components will cancel out each other. So this is what is the final answer, or this is what is the procedure of solving such questions. Right, you will face such questions multiple times. Okay? These are the typical type of questions that you will get. Right, these are the typical type of questions you will get here. Sure. So yes, this is about this is entirely about the momentum conservation and what is how do we do that and the mass moment conservation. So there are a lot of questions which we can do. Just let me check if we have done some similar questions in this one. If at all we have, I will not continue doing that. If not, then we can definitely try and solve those questions. So yes, we have done such a question, right? So I explained you now how exactly we can do this. And this is the mass moment conservation. Yes, very good. We've already done all of that. All right. So let's now try and speak more about how do we find the position of center of mass. Right? How do we find the position of center of mass? Right. So in the previous lecture, I've already spoken about finding the position of center of mass for discrete mass system. I've spoken about for a discrete mass system. Now, what if the mass system is not discrete? Instead, it is a continuous mass system. Right? What if the entire mass system is continuous? What do we do in such a case? Let's try and analyze that. Okay, let's try and analyze that. How do we find the position of center of mass of a continuous mass system? So just a reminder that we do free basics lectures every day at 11 a.m. on this channel, IITP Classroom. So if you have not subscribed to this channel yet, please do subscribe and also hit the bell notification so you will get notified whenever we are live. So yes, let's try and understand how do we find the position of center of mass of a discrete, of a continuous mass system. We need a position of center of mass of continuous mass systems. All right. Now, for a discrete mass system, I've written that it is summation MIRI, right? So if let's say there is a continuous mass system, uh, so these are the coordinate system. These are the coordinate axes. And this is some mass system. All right. So what I do is I take now this is a continuous mass system, right? So I let's say I take some dm mass here, right? Some dm mass here, whose position vector can be given by this vector. This vector represents its position. Right? This vector represents its position. So this vector represents its position. Let's name this vector as r vector. So what I can do is I can break this continuous mass system. Let's say the mass of the system is m. I can break this continuous mass system into small particles, but I cannot break them into discrete masses. right? I cannot break it into discrete masses because it is continuous mass system. It cannot be broken down into discrete masses. So we cannot have different masses here. It is a continuous mass system. So if there is a continuous mass system, right? If there is a continuous mass system, I have taken a small part of that continuous mass system, dm mass. I've taken a small part of this, which is the dm mass, and now that dm mass is located at a position r. Right? It is located at a position r. So what I can say is the position of center of mass in a discrete mass system. Now, for discrete mass system, we would have added all of those masses positions and divided it by total mass. But here we cannot add it. Here we cannot add it. So what we need to do is we need to integrate. So integral dm into r upon integral dm. That is what we are going to write here. That is what we are going to write the position of center of mass as. This is how the position of center of mass will be calculated. This is how the position of center of mass will be calculated. Right, it is integral dm into r upon integral dm. Right. What is r here? What is r here? It is very important to understand what is r here. Right. dm is the mass of an element. And what is r here? R is the position of center of mass of dm element. So this entire continuous mass will be broken down into small elemental masses, and those elemental masses will then be added up to get the entire mass and the position of the center of mass likewise. All right. So dm is the element and r is the position of the center of mass of that elemental mass dm. Right. So how do we break it down? Right. What are the elements that we take? So I would say, what is the mass system like or mass distribution like? And what will be the corresponding elemental mass be like? Right. So if the mass distribution is linear, that is mass is distributed along a line, then the element will be a point mass. Right. Similarly, if the mass distribution is surface, then the element will be a linear mass distribution. And if the mass distribution is volumetric, then the element will be a surface mass. Right? So for example, if I were to write the examples of each, I would say if the linear mass distribution is rod, so I would take point masses. If the surface mass distribution is, let's say, a disk, I can treat it like infinitely many rings together. Right? If the volumetric mass distribution is, let's say, a solid sphere, then I can take the surface distributions as hollow shells or probably disks or anything. Right. So this is how we are going to calculate, or we are going to break it down into different mass distributions, elemental masses, and then we can calculate the position of center of mass for each of these mass distributions. All right. So we shall continue our discussion on this part in the next part, in the next class, right? So till then, subscribe to the channel, keep sharing, keep liking this videos, and it will motivate us to give you more content here on YouTube for free. That is it from my side. Take care. Have a good day.